Welcome everybody. I'm going to take a look at just a refresher on what we did in all of Term 4 here. So Term 4 included Chapter 7, 11, 12, 13, and 20 here. So we started with circular motion. We did the momentum stuff in the previous chapter, so that won't be on this assessment. So to begin with circular motion, we started by talking about centripetal acceleration and centripetal force. Just need to remember there, centripetal is just a direction. That means toward the center of the circle. Centrifugal would be away from the center of the circle. We have equations for the acceleration and the net force toward the center of the circle for anything that's moving in a circular path. We also had this idea of centrifugal force, and we talked about how that's really misused most of the time. Centrifugal force is a fictitious force that only exists in a rotating frame of reference. So we're just going to avoid that problem and not talk about centrifugal force at all for explaining, for example, why something gets flung to the outside of the container, like the ride at Adventureland, where you stick to the wall. It's not centrifugal force it's flinging you outward, it's your inertia trying to make you go in a straight line. And the force that's acting on you is a force toward the center of the circle from the wall that causes you to go in the circular path, because otherwise you'd go in a straight line path. Also in Chapter 7 we talked about gravitation. So the gravitational force and the law of universal gravitation that says that all objects attract each other by this force of gravity, and it depends on their masses and the distance between them. We talked about orbit and the amount of time it takes to do one orbit, the orbital period, and the orbital speed, how rapidly we go around in orbit. We looked at the idea of weightlessness and how when you're in orbit and you feel like you're floating, or you are floating around, you're not really weightless, you're just in free fall, falling at the same rate as everything around you. Also in Chapter 7, this was a big chapter, we looked a little bit at torque, the ability of a force to cause rotation. We looked at mechanical advantage, that's how much a force is multiplied by when we use a simple machine. And then we talked about efficiency, how much of our energy makes it to the desired form, and how inefficient a lot of our machinery is. We get all this heat produced when we're trying to, say, move a car forward. The next chapter was simple harmonic motion and waves. So we started off with Hooke's law. That was the one that related the force that a spring exerts on some object and the distance that spring is stretched, so that it was proportional by this factor k that we call the spring constant. The definition of simple harmonic motion, that's the periodic motion or repetitive motion that occurs because we have a restoring force. That's a force that points toward equilibrium all the time. A restoring force that gets larger as displacement from equilibrium gets larger. So it's proportional to displacement. With simple harmonic motion, you need to be able to discuss the points of the greatest and the least displacement, velocity, acceleration, and force, and talk about the frequency and period for a simple harmonic oscillator. Both talk about those and make calculations with those. Later on in that chapter, we started our stuff with the waves, and that takes us through the end of the unit. So we did types of waves to begin with, transverse waves or longitudinal waves. The longitudinal ones, remember, are also called compression waves, or so sound waves are an example of longitudinal waves. Wavelength, wave speed, and frequency. We have the equation, the wave equation that relates those three. The factors that influence wave speed and the factors that don't influence wave speed. You need to have a good grasp on those for the test. The idea of interference and superposition. So that's when we have these two waves that overlap each other, they add together to make a bigger wave, or if they're bumps in the opposite direction of each other, then they add together to make a smaller wave, but it's just an addition of the amplitude of the two waves that we use to determine how big those waves are. and standing waves. So you need to be able to recognize the shape of a standing wave, figure out what the wavelength of a standing wave is in relationship to the length of the string or the tube that it occupies. That comes back up in sound, which is what Chapter 12 was about. So how do we produce sound waves using vibrations, that kind of thing. The Doppler effect, the idea that we have this frequency shift that's an increase in frequency when something moves towards you and a decrease in frequency when it moves away from you. Intensity of a sound, that's the power divided by the area of the sphere over which that power is spread. So power over 4 pi r squared. This is one of the inverse square laws. As we get farther away, the intensity of a sound decreases with the square of the radius, or decreases as the square of the radius increases. Musical instruments kind of ties back to standing waves. We had string instruments, open pipe instruments, and closed pipe instruments. We had some equations that went with each of those. Beats, that happened when we had two sounds that were played together that were very, very close in frequency, and we hear that oscillation and loudness, that wah, 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 wah. So knowing about the beat frequency would be important for that. Chapter 13 was about light, and this was our most recent unit, so probably freshest in your mind. We talked about the electromagnetic spectrum, so radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays are on the electromagnetic spectrum. They're all the same kind of thing, just different frequencies, different wavelengths. They all travel at the same speed as well, 3.00 times 10 to the 8th meters per second. We talked a little about reflection and the law of reflection. This happens when a wave bounces off a surface. It's going to bounce off at the same angle that it hit at. For plane mirrors, we can use that to create always virtual images, always behind the mirror, and always the same distance behind the mirror as the object is in front of the mirror. For spherical mirrors, we did the lab where you had some experience with, and when I place the mirror here and the object here, what kind of an image do we get? Is it a real image or virtual? Is it upright or inverted? Is it larger than the object or smaller than the object, etc.? And then for color, the idea that we primarily see red, green, and blue light, or those are the colors that we see the best anyway. We can fool our eyes and our brains into thinking there are colors present that aren't really there by shining multiple colors of light together. So if I take a yellow object and I illuminate it with only red light or only green light or only blue light, what color is it going to look in those different lights? So you need to be able to do that for the test. And then Chapter 20, electromagnetic induction. We didn't do anything with that. I was just messing with you a little bit. Sorry about that. Anyway, have a great night, and I will see you tomorrow for the final exam. Bye-bye.